Welcome everyone to our first lesson of Unit 4B, Systems of Linear Equations. So as you can tell, this one is a play posit, but future ones will also be live because I want to make sure that I can answer your questions on the spot. So today our goal is to think about what is a system of equations, specifically linear equations, what it means to be a solution to a system of linear equations, and how to solve a system of linear equations by graphing. So without further ado, let's get started. So here are three definitions, and I'm about to put in a pause because I want you to write them down in your notebooks. They're going to be very important, and you're going to be doing an exploration in a moment by seeing, can you apply the definition to be able to figure out the answer? So I've already highlighted them in red, but it's a system of equations, a system of linear equations, and a solution to a system. So I'm going to pause it to give you guys a chance to write it in your notebook. Okay, so hopefully you have those written down. And now let's see if you can put them to practice. So here's your first exploration. I want you to take no more than 5 minutes. Using the definition of what it means to be a solution, is -3, 5 a solution to the system of linear equations made of the two equations below? So you have 5x plus 2y equals -5 and y equals 5x plus 19. So give it a shot. So the idea of a system is the x that is here must be the same x that is there. And we're looking for the same y for both of these, something that satisfies both. Well, here's our y, here's our x. So by asking if -3, 5 is a solution, well, we have to see if it makes both true. So let's see, 5 times -3 plus 2 times 5. Well, our wonder is, does it equal -5? Well, -15 plus 10, -5, in fact, does equal -5. So this is a solution to the first one. That's a definition we've used before. Solution means, does it make it true? It makes the first one true, but for a system, it must make all of the equations in the system true. So let's try the next one. 5 equals a 5 times -3 plus 19. 5 equals, maybe, we'll put a question mark there, -15 plus 19. 5 equals 4. Well, that's not true. So -3, 5, just because it works for the first one, it doesn't work for the second one in this case, is not a solution to the system. It's not good enough to make one true. It must make all of them true. Okay, so let's practice that a little bit. So is 4, 10 a solution to the following system of equations? Give it a shot. Hopefully you found that it is not a solution because, again, it worked for the first equation, but it didn't work for the second equation, and therefore it is not a solution to the system. All right, here's another practice problem. Let's see if -6, 5 is a solution. Just as a reminder, the equation on the left is in point slope. The equation on the right is in standard form. Go ahead. So when we plug this one in, well, we saw that the left side of the equation in both results in the right side of the equation. Both equations are true. So -6, 5 is a solution to this system. So we're starting to think about what it means to be a solution. It's finding an ordered pair that satisfies both. Now, there's three methods of solving systems of linear equations that we're going to look at this year: graphing, substitution, and elimination. Today, our focus is on graphing. So let's take a look at what that looks like. So here's an exploration for you to start first, though. I want you to graph both of the following equations on a single graph. So I only have one here. And based on the graph, what do you think the solution of the system is? So go ahead. So I'm going to color code mine. So I'm going to do this one in green. So I'm going to start at the y-intercept of 1. I'm then going to, well, that's negative 2 over 1. So down 1, 2 over 1, 1, 2 over 1, 1, 2 over 1. You're going to see why in a moment. I'm actually doing more. So I can go backwards to up 2 over 1. Just continue the pattern in the other direction. You're going to see why I did that. Then I'm going to graph this one. That's also in slope-intercept form. So I can start at a 4. And that's a slope of 1 in front of it. So up 1 over 1. But I can also go backwards to there. Well, according to the graphs, each one of these ordered pairs on it is a solution. So I need to find an ordered pair that both of them have. And that means that's the solution. Well, it's right here, negative 1, comma 3. Both graphs go through it, which means negative 1, comma 3 is a solution to both. So negative 1, comma 3 is the solution to the system. We can see that, say this ordered pair right here, 0, comma 4, that only is for a solution for the orange line. I need something that's a solution for both. So it ends up being what we call this point, the point of intersection. So when looking at a system by graphing, we want that point of intersection. So here's a practice problem for you guys to try. So give it a shot. So here is my graph for this system. Hopefully you can see why sometimes I have to work backwards. So for example, for my green line, instead of going up 5, because rise 5, run 4, I can actually go backwards. So instead of rising 5, I go down 5. Instead of right 4, I go left 4. Because if I go backwards, I'm sticking with the same pattern. And this is what I end up finding as my solution. Okay. Now, here's a practice problem. Now I'm going to give 2 hints. Convert the equation to slope-intercept form, or find the intercepts. I saw some of us had difficulty with this on the last question of the summative, determining if a relationship was parallel or perpendicular. I'll help with the first one. So all of a sudden, I have x plus 3y equals 9. I can subtract x and get 3y equals negative x plus 9. Divide by 3, divide everything by 3. That's a y equals, well, that's a 1. So that's a negative 1/3 x plus 3. I'm now in slope-intercept form and can graph it using that. We have a y-intercept of 3, down 1 over 3, the opposite up 1, back 3, and there's my graph. So you do the second one. So as I was saying, we can put it into slope-intercept form to determine the slope and the y-intercept. This takes only a step to do it. So now all of a sudden, I'm going to say, okay, negative 2. And I go down 1, 2 over 1. So that means I go up 2 over 1, up 2 over 1, up 2 over 1. Because I went all the way back to find where they intersect, which happens to be at this point. I'm going to use point of intersection, POI. So therefore the solution is -3, 4 is the solution to the system. You can check it too. Feel free and check it. So I'm going to plug in -3 for x plus 3 times 4. That's a -3 plus 12, which is a 9, which satisfies this equation, because therefore 9 equals 9. Well, the other one, 2 times -3 plus 4. Well, let's see if it equals -2. -6 plus 4 equals -2. -2, in fact, equals -2. So it is the solution to both. All right. This one, you do all on your own. Comes with a little twist, though. Go ahead. Well, they didn't intersect. Well, I guess that actually, it makes a little sense because, well, when I rewrote it in slope-intercept form, that slope is -3. That slope is -3. And they have different y-intercepts. So they're parallel. So never will intersect. So what's the solution to the system? No solution. They will never intersect. They will never have an ordered pair that will satisfy both. So this allows us to draw a conclusion, is that the possible solutions for a system of linear equations is 1, no, or infinite solutions. So I'm just going to draw 3 small graphs to give examples of them. Now, one solution is what we saw a lot of. The idea is we have one graph intersecting another, and there's the solution right there. And so if the linear functions have different slopes, there will be one solution. Different slopes means they are going to be changing the order in which they're rising and running. Well, what we just saw with no solution is if the functions are parallel, have the same slope, but different y-intercepts, and you're going to see that in a second, then no solution exists. Well, I specified that on purpose because if all of a sudden, for infinite solutions, if I have the same slope and same y-intercept, they are the same line and share infinite solutions. If we think about it, here's my green one. If my orange one has the same slope, same y-intercept, it's just going to land right on top of the green one. So the two lines are on top of each other, which means they intersect infinitely. So there's infinite solutions. So to finish up this play posit, there's going to be a couple questions asking you whether there's one, none, or infinite solutions. Think about what allows you to determine that. And other than that, see you for the next class live. Bye, guys.